Hello, and welcome to Mrs. Law's class. In this lesson, we're going to take a look at conditional probability. Now, given two events A and B over the same sample space S, the probability that event A will occur, given that B has occurred, is called the conditional probability. And that is of A given B. And it is denoted or written by probability of A, and then we draw a straight line, and then B. So probability of A given B. So let's take a look at the reasoning. Consider this Venn diagram. We have two events A and B, and they're overlapping. So let's say that event B has occurred. So I'm going to shade this in to say that event B has occurred. Then therefore, the probability of A given B means the extent to which A is contained within B, since the sample space is now reduced to B. So that would then be, I'm going to erase this part, just this middle part, because we have only event B, and then the probability of A, given that B occur, is only this overlapping part. So if A and B are dependent events, then we have that the probability of A given B is equal to the probability of A and B, which is that middle part where it's shaded in, divided by the probability of B, because our sample space has now been reduced to B. Now this is referred to as Bayes' formula by a mathematician named Thomas Bayes. So the denominator represents the total probability, or the sum of all the possible branches if we drew a probability tree. Now, if the two events A and B are independent, then we have the probability of A given B is equal to the probability of A times the probability of B, because probability of A and B are independent. And this would all divide by the probability of B. However, now, the probability of B will cross off in the numerator and the denominator, so then we're only left with the probability of A. And that's because if they're independent, that means that one does not depend on the other. So it doesn't matter if B has happened, P of A, or the probability of A, will still occur. Now, to help you solve conditional probability problems, I recommend that you draw a tree diagram so that we can take a look at all the different branches. Let's take a look at an example to illustrate this. A company has two factories that make computer chips. Suppose 70% of the chips come from factory 1. So I'm going to draw a tree to represent this. So we have factory 1 and factory 2. So 70% come from factory 1 and 30% come from factory 2, or 0.7 and 0.3. So in factory 1, 25% of the chips are defective. So we're going to branch out for factory 1. So those are defective, I'll call it D, and that would be 0.25. And those are not defective, I'll put D with a line on the top and put 0.75. While in factory 2, only 20% of the chips are defective. So D and D with a line, the complement. So you have 0.2 and 0.8. Now, suppose it is not known from which factory a chip came from. So the question is, what is the probability that the chip is defective? So we can say that the probability the chip is defective is equal to the probability that it is from factory 1 and it's defective, or we can say that it's the probability of factory 2 or it came from factory 2, and it's defective. Now, if we write this out formally, this is what it would look like. The probability that it's defective is equal to the probability that it's from factory 1 times the probability that it's defective given that it's from factory 1 plus the probability that it's from factory 2 times the probability that it's defective given that it's from factory 2. Now that's kind of really a bit long-winded, but really what it means in terms of the numbers is that probability that's from factory 1 is going to be 0.7, and then probability that it's defective given that it's from factory 1 will be 0.25. That means that we have to follow the branch from factory 1. So that's 0.25, and then factory 2. So the probability that's from factory 2 is 0.3, and then times the probability that it's defective given that it's from factory 2 means that we follow the factory 2 branch. So that would be 0.2. So typing everything into our calculator, we get 0.235. Now let's take a look at a question that involves conditional probability. Suppose that a defective chip is discovered. That also means if a defective chip is discovered, or given a defective chip is discovered, what is the probability that the chip came from factory 1? So we want to find the probability that the chip is from factory 1 given that it's defective. Now we know that it's in this order because the question says, what is the probability that the chip came from factory 1? And that is what we write first. So the probability that it came from factory 1 given that it's defective is equal to the probability that it's from factory 1 and defective divided by the probability that it's defective. So this is equal to, so if it's from factory 1 and it's defective, that means it's going to be 0.7 times 0.25. And if you look above, that's this part here. And then we divide by the probability that it's defective. So a defective chip, remember, can come from factory 1 and factory 2. So we're going to use this number 0.235 as our probability of being defective. So we multiply this out, we get 0.175 divided by 0.235, and then when we divide, we get 0.7447, which seems a little bit high, but it's not, because remember, most of the chips come from factory 1, and then there are more defective chips from factory 1 than there are from factory 2. Let's take a look at another problem. So this is quite a common one that you'll see quite often. A test is 97% accurate that a person who tests positive actually has the disease. If 2% of the population has the disease, what is the probability that a person selected at random actually has the disease if he or she tested positive? All right, we're going to start with a little let statement so that we know what everything stands for. So we're going to say let D equals has the disease. And then we're going to let T equals test positive. Because it actually says here, was probably selected at random actually has the disease if he or she tests positive. So we're going to draw our tree starting with our population. So D, and then D with a line on the top. So 2% have the disease, so 0.02. And then therefore 0.98 do not have the disease. All right, now we're going to talk about the testing part. So we have test positive and does not test positive. So if the person has the disease, they should test positive 0.97 or 97% of the time. They don't test positive or they test negative, that would be 0.03. Now, this is a little bit tricky, but if they don't have the disease, then the probability then that they don't test positive, that should be accurate because the 97% is referring to the accuracy of the test. So if they don't have the disease, then they should be testing negative. So then, therefore, the 0.97 actually goes on testing negative because they don't have the disease. So therefore, testing positive would be 0.03, which is actually inaccurate because they actually don't have the disease. So let's write a little note about that in case we forget. So if a person does not have the disease, the person should test negative accurately. All right, let's go back to the question. So what is the probability that a person selected at random actually has the disease? So probability of having the disease if he, she, or test positive, given they test positive. So that equals the probability of having the disease and testing positive divided by the probability of testing positive. So the probability of having the disease and testing positive is 0.02 times 0.97, which is this branch over here. And that's divided by the probability of testing positive. Now there are two ways to do that. So one way is the 0.02 times 0.97, which is having the disease and then testing positive. Or we can not have the disease. So we're going to add not have the disease, which is 0.98, and then we're going to multiply that by 0.03 because they still tested positive even though that is not accurate. So in the numerator, we get 0.0194. In the denominator, we get 0.0488. But you can type all of this out together at one time, and you get 0.398. And that's how you do a conditional probability problem.